This is Year 13 AS2 Physics 2, and this is past paper answers to superposition and interference from 2004 to 2009. So the first question, state the essential conditions for the formation of a stationary wave. Now you know that a stationary wave is formed whenever two waves meet each other passing in opposite directions and they interfere. So you have to have waves travelling in opposite directions. And they have to interfere with each other. Now there's another condition for you to observe a pattern, and the other condition is to make sure that they have a constant phase difference, or in other words that means that they have the same frequency. You could say wavelength, or you could say speed there. The same frequency, or you could say a constant phase difference. There's a number of ways of saying that. Now this question comes up quite often, and these are the things you need to get your 3 marks. It is normally worth 3 marks. They have to be travelling in the opposite direction. They have to interfere with each other, and they have to have the same frequency or a constant phase difference. And you'll see that again in another question. Right, part B then. Figure 4.1 shows a signal generator connected to a loudspeaker L. So there's a loudspeaker and there's a signal generator. A pure note is emitted from the loudspeaker. A small microphone M is connected to a correctly adjusted cathode ray oscilloscope, and it's placed in front of the loudspeaker. Sketch the trace that would be displayed on the cathode ray oscilloscope. So because the sound is a wave, the microphone transmits a voltage to the cathode ray oscilloscope and it displays it as a voltage. So it picks up the sound and transmits it as a voltage. And that voltage will come up as a sine wave like that. As a sine wave like that. A flat board with a surface, which is an excellent reflector of sound waves, is placed in the path of the sound waves from L. Stationary waves are formed in the space between R and L. So right along here, there are stationary waves being formed. Okay, all along there. Figure 4.2 shows the arrangement. The small microphone M is moved along the line between R and L. Describe how the trace on the CRO would change and explain why the changes take place. Now, as you move your microphone between R and L there, what you're going to do is pick up positions of large amplitude, small amplitude, large amplitude, small amplitude, the whole way along there. And that, therefore, will be your trace here. You'll always have this trace, but it's going to get smaller whenever you come to a note and larger whenever you get to an antinote. So you're going to continually have a large trace, a small trace, a large trace, a small trace. And so you have to try and describe that and get yourself 3 marks from it. So first thing we'll say is that the amplitude would increase and decrease. And we'll say repeatedly as you move. As M moves from R to L. So why are you getting that? And the reason that you're getting is when you have maximum amplitude, there is constructive interference going on. In other words, if I just show you the diagram there, you've got a wave coming down from the loudspeaker and one being reflected from the sheet here, and there are positions where they are constructively interfering and causing a maximum amplitude, and the microphone's picking that up. And then obviously I'm going to explain that then you have positions where they're actually cancelling each other out, and there you're getting destructive interference. So when you have minimum interference, when you have minimum amplitude, and you get antinodes there, I should have written. And when you have minimum amplitudes, you're getting destructive interference. And you're getting nodes. Now it really might be a good idea if you learnt a decent answer like that, to answer a question like that, because that would be a fairly common kind of question as well. Part C then is the calculation. A tight string of length 0.9 metres is clamped at both ends. Vibrations of frequency 180 Hz are initiated in the string. The string vibrates as shown in figure 4.3. Calculate the speed of the progressive waves which give rise to this mode of vibration. So you can see there in total you've got 1.5 wavelengths, and you know the length of that is 0.9 metres. So therefore you can work out lambda. Lambda is 0.9 divided by 1.5, and that gives you 0.6 metres. So you know the wavelength. And then it's just a simple matter of doing V is equal to lambda F, and that's 0.6 times 180, and that gives you an answer of 100. Gives you an answer of 108 metres per second.